So today we are going to learn about the hydrogen molecule, H2 molecule. Okay, H2 molecule. Let us first understand what are the constituent particles in the hydrogen molecule. In hydrogen molecule, there are two nuclei. That is nucleus A. This is the nucleus of a hydrogen atom. And there is another nucleus, that is nucleus B. This is the nucleus of the hydrogen atom B. And there are two electrons also. One electron is designated as electron 1 and the other electron is designated as electron 2. Okay, therefore this is a four particle system. And the distance between the nucleus A and the nucleus B as usual is R, capital R. Okay, and the distance from the nucleus A to electron 1 is RA1, and the distance from nucleus B to electron 2 is RB2, and the distance from the nucleus A to electron 2 is RA2, and the distance from electron 1 to nucleus B is RB1, and the distance between electron 1 and electron 2 is R12. Okay, this is how we have defined the system. So we have two nuclei and two electrons, and there will be interaction between these two nuclei and two electrons. There are many kinds of interaction. First is the nucleus repulsive interaction. Then there is electron 1, electron 2 repulsive interaction. There are attractive interactions also. Nucleus A, electron 1 attraction, nucleus A, electron 2 attraction, and nucleus B, electron 1 attraction, and nucleus B, electron 2 attraction also. So there are attractive terms and repulsive terms in the Hamiltonian. So this Hamiltonian, we will define the Hamiltonian in the beginning itself. The Hamiltonian for this system, H cap, is equal to minus half del 1 square, minus half del 1 square. This is for the kinetic energy operator for the electron 1. Okay, the Hamiltonian is written in the atomic units. That is why it is written minus half del 1 square. Otherwise, we have to write like minus h square divided by 8 pi square and del square like that, del 1 square like that. So here we have written that in atomic units. So minus half del 1 square. And then the kinetic energy operator for the electron 2, that is minus half del 2 square. And then comes the attractive potential energy terms. So the first one is minus 1 divided by RA1, that is the attraction between the nucleus A and electron 1. Okay, so attractive potential energy operator is minus 1 divided by RA1, and then minus 1 divided by RA2. RA2, this represents attraction between nucleus A and electron 2. Then comes minus 1 by RB1, and then minus 1 divided by RB2. Okay, so these are the attractive potentiality terms in the Hamiltonian. And then comes the repulsive terms. So we give plus sign. First of all, let us write the repulsion between electron 1 and electron 2. Then this is divided by 1 divided by R12. Then the nucleus repulsion, that is 1 divided by R. Okay, all these expressions are similar because all these are expressed in atomic units. So this is a Hamiltonian for the system. Obviously, it's a very big Hamiltonian. Okay, so solving the Schrodinger equation for this system is not going to be easy. Actually, it is not exactly solvable because of the electronic repulsion term in the Hamiltonian. Okay, this term is the problem, and therefore we can again take this Hamiltonian as H cap H cap is equal to H cap 1, H cap 1, okay, where H cap 1 actually is, I will indicate those terms here. H cap 1 is minus half del 1 square, this one, that is the kinetic energy operator for the electron 1, and then minus 1 by RA1, okay, and then minus 1 by RB1. These are the terms for electron 1, okay. So H cap is equal to H cap is equal to H cap 1, where H cap 1 is equal to minus half del 1 square minus 1 by RA1 minus 1 by RB1, that is H cap 1. We write it here, it will be clear then. H cap 1 is equal to minus half del 1 square minus 1 by RA1 minus 1 by RB1, okay. Actually, what is that? What is that? This is the um, operator, Hamiltonian operator. If we are considering this system, means we have two nuclei here. We consider like this: nucleus A and nucleus B here, and then we consider only electron one. Electron one. Okay. In this case, there are only electron repulsion. Okay, this is R, and this is the distance is RA1, and this distance is RB1. Okay, so if we are considering the Hamiltonian for this system, then the Hamiltonian will be the kinetic energy part minus half del 1 square. Then the potential energy part, potential energy due to attraction, that is minus 1 by RA1 minus 1 by RB1. Okay, and there is one other potential energy term 1 by R that we will consider later. It is already here. Okay, so to all these three terms together will constitute the Hamiltonian for this system, okay, except the interelectronic repulsion term. So avoiding the interelectronic repulsion term from the Hamiltonian is normal. You know this from the Born-Oppenheimer approximation, because the two nuclei are kept at a fixed distance when we are considering the Born-Oppenheimer approximation. Therefore, you can conveniently avoid 1 by R from the Hamiltonian and then solve the Schrodinger wave equation. Whatever may be the change which will occur in the eigenvalue due to this 1 by R term in the Hamiltonian will be added later. You know already this from the Born-Oppenheimer approximation. If you don't know this, you go back to my lecture on Born-Oppenheimer approximation, where I am describing how 1 by R term can be kept out of the Hamiltonian while solving the Schrodinger wave equation. So therefore, these three terms together constitute the Hamiltonian for this system. What is this system actually? That is H2 plus, right? H2 plus. Two nuclei of hydrogen, and there is only one electron. That is H2 plus. We have already learned that. Therefore, H cap 1 is actually the Hamiltonian for the H2 plus system. H2 plus system, where we are considering the electron 1. So this is the H2 plus system with electron 1, the Hamiltonian for this. So this can be considered as a core Hamiltonian. Okay, and then we take the other terms. Let me take the red lines to indicate those terms. Minus half del 2 square, then minus 1 by RA2 and minus 1 by RB2. These three terms together constitute another H2 plus with the electron 2, right? Therefore, we can write this as H cap 2, H cap 2. So that is the core Hamiltonian with an H2 plus system which contains the electron 2. Okay, so H cap 1 plus H cap 2, and then what is remaining? All these terms are taken, and what is remaining is 1 divided by R12 plus 1 divided by R. Okay, so this is a Hamiltonian. So here H cap 1 and H cap 2, you already know. This represents the electronic Hamiltonian for H2 plus ion with electron 1 or electron 2. Okay, So this is a Hamiltonian for the system. And now we are going to consider the functions. Okay, we are going to consider the functions. And the wave function we have to consider here like this. Let me bring the screen down. Yeah. So I'm going to consider about the wave function. Here we are considering the H2 molecule as an electron plus one electron plus an H2 plus system. Okay, so that gives the H2 molecule. We consider the H2 molecule like that. Means we are adding one electron to the already known H2 plus system. We already know about this H2 plus system. We had a series of lectures on this system. So we know about the eigenfunctions, and we know about the energy values for the H2 plus system, and we know the energy profiles, how the molecular, how the bond length can be approximated for the system. All these things we know. So since we know already this system, H2 plus system, we are going to do, we are going to add one electron to this H2 plus system to create the H2 molecule. This is just an approximation. This is not very accurate. Okay, I will tell you why this is not very accurate. Um, because when you are considering the H2 plus system, you are not considering the inter-electronic repulsion, and then you are adding one electron to that system. Means we are adopting the atomic orbitals of the H2 plus system, and then we are placing the electrons in that one. Okay, there is some problem with that. I will explain that. Don't worry about that. So we are considering the H2 molecule as an additional electron added to the H2 plus system. So what we are going to do here is that we are going to take the atomic orbital of the electron, atomic orbital of the H2 plus system. Okay, you already know the atomic orbitals of the H2 plus system. In the last lecture, I denoted the ground atomic orbital of the H2 plus system as sigma g, that is the ground atomic orbital. Okay, ground state atomic orbital, or the atomic orbital of the lowest energy. Okay, and this there were two atomic orbitals, like not atomic orbital, the molecular orbital, sorry, the molecular orbital. So we are taking the molecular orbital of this 2 plus system, that is a ground molecular orbital of this 2 plus system, and there is excited, there is a higher molecular orbital also, that is sigma star, that was an anti-bonding molecular orbital. So what we are going to do is we are going to hire this molecular orbital of the H2 plus system. Okay, and then we are going to place both of our electrons in the hydrogen molecule. Okay, this is a two electron system. Two electron system. Both these electrons will be added in this sigma g. Okay, because one orbital can accommodate two electrons. So that is why we are going to constitute the wave function. So the wave function for the H2 plus system psi is equal to sigma g1 sigma g2. It means that both electron 1 and electron 2 are in the sigma g molecular orbital of the H2 plus system. We are higher in this molecular orbital. Okay, and we are placing both electrons here. And there is a problem here, and when we are placing both electrons here in this sigma g orbitals, there's a problem. This sigma g orbitals expression, we have created the expression for the sigma g orbital based on this type of a Hamiltonian. We used this Hamiltonian, then only we got the expression for the sigma g, right? In this Hamiltonian, something is missing. What is missing in this Hamiltonian is this term 1 divided by R12, means the inter-electronic repulsion term is missing in this Hamiltonian. Okay, so this sigma g orbital, which is being adopted here, is not a complete representation of an orbital in which the two electrons are accommodated. Sigma g orbital is an orbital where only one electron is accommodated, and this expression for the orbital actually lacks the properties which would have been occurred if we adopted a Hamiltonian, which would also include the interelectronic repulsion term. അല്ലെ? ഇപ്പൊ ഇന്റർഇലക്ട്രോണിക് റിപ്പൾഷൻ ടേംസ് ഒന്നും ഇല്ലാത്ത ഒരു ഹാമിൽട്ടോണിയൻ ഉപയോഗിച്ചുകൊണ്ടാണ് നമ്മൾ സിഗ്മ ജി ഓർബിറ്റൽസിന്റെ എക്സ്പ്രഷൻസ് നമ്മൾ ഉണ്ടാക്കിയെടുത്തത്. അങ്ങനെയുള്ള ഒരു ഓർബിറ്റിലേക്കാണ് നമ്മൾ ഇലക്ട്രോൺ 1നെയും ഇലക്ട്രോൺ 2നെയും നമ്മൾ ആഡ് ചെയ്തത്. സോ ദർ ഈസ് എ problem in adding this, but as a first approximation it's okay. So that is why I said that this is not a completely reliable method which is going to give you very accurate results, but this is an approximation. It's a good approximation for the beginning. Okay, so we are adopting or we are hiring these molecular orbitals from the H2 plus system and then placing both electrons in this H2 plus system. Okay, so that is how we have constituted the psi. Now there is a problem to constitute the wave function like this. The problem is the Pauli's exclusion principle. The Pauli's exclusion principle states that for you already know the Pauli's exclusion principle. The Pauli's exclusion principle that you already know is very simple definition, and the definition says that no electrons in an orbital can have, or in an atom can have, the same set of all the quantum numbers. Okay, no two electrons in an atom can have same set of all the 4 quantum numbers. So electron 1 and electron 2 cannot have all the same set of 4 quantum numbers. So the set of quantum numbers should be different. Okay, if we are strictly speaking this Pauli's exclusion principle, we can also say like for a system of 2 or more electrons, the complete wave function including the spin must be antisymmetric with respect to interchange of any 2 electronic positions. I write like this because you have not heard this definition of the Pauli's exclusion principle. For a system of 2 or more electrons, for a system of 2 or more electrons, the complete wave function including the complete wave function including the spin, must be antisymmetric with respect to interchange of any 2 electron positions. Okay, you may be wondering what does this mean. I'll explain. Okay, so we have the Pauli's exclusion principle like this, and the Pauli's exclusion principle. Okay, this is Pauli's exclusion principle. Okay, so Pauli's exclusion principle states that for a system of 2 or more electrons, a complete wave function including the spin must be antisymmetric with respect to interchange of any 2 electrons. Here you can look at this wave function. This wave function only gives, if you are taking the square of this wave function, it will only give the probability to find the electron in a specific position, right? But this wave function is not complete. Why I said that this wave function is not complete? Because the wave function must not only explain the probability of finding the electron in a specific point in space, but it should also give the probability that the electron is in one or the other spin state. So these 2 electrons will have its own spin state. Okay, that is an inherent property of the electron. So it can have the alpha spin or beta spin. So the wave function must also explain that. The wave function should also say that the electrons, the probability for the electron 1 and electron 2 to have for the alpha spin state or beta spin state, the probability that the electron is in the alpha spin state or in beta spin state, that also should be explained by the wave function. So this wave function, what is written here, is an incomplete wave function. So the complete wave function must explain the spin state of the system also. Okay, so I will write the complete wave function here. Psi is equal to sigma g1 sigma g2. Then we have to explain its spin. We have to explain its spin also. So the spin can be spin of the electron 1 and electron 2 can be alpha or beta. So there are different possibilities. Okay, so one possibility is the electron 1 has alpha spin state and electron 2 also has alpha spin state. So we write it as alpha 1, alpha 2. And the second possibility is that, this is first possibility. The second possibility is that sigma g1, sigma g2 and electron 1 and electron 2 both have a beta spin state. So beta 1, beta 2. And the third possibility is that sigma g1, sigma g2, then first one has alpha spin and the second one has beta spin. So alpha 1, beta 2. Okay, alpha 1, beta 2. Now there is a problem that if we are taking the square of this wave function, okay, square of this function, you will get some particular value, sigma g1, sigma g1 square, sigma g2 square, alpha 1 square, beta 2 square. But now you just suppose that the two electrons here are being exchanged, means the electron 2 takes the alpha spin state and electron 1 take the beta spin state, means just the electrons reverse their spins. Okay, so if the electrons reverse their spins, actually nothing should happen to the system because the two electrons are indistinguishable, right? So even if the two electrons are reversing their spins, the state, since the two electrons are indistinguishable, there should be no change in the square, because square is going to define you the probability to find the particle in space plus probability that the electron can be in either the alpha spin state or beta spin state. So even if the electrons are exchanging their positions, you should get the same probability. But if you are taking the square here, you will get alpha 1 square, beta 2 square for the first possibility. But after exchange, you will get alpha 2 square, beta 1 square, alpha 2 square and beta 1 square. So the value will be different, right? So after exchange, if you are taking after and before exchange, if you are taking the square of the function, you will get a different values for the square. So that is not going to be correct because electrons are indistinguishable, and the exchange of the electron should alter it to alter the value of the square of the function. So there is some problem to write it like this. So we have to write it like a linear combination of this one. So what we are going to write is we are taking both possibilities and then take the combination of both. Means alpha 1 beta 2 plus alpha 2 beta 1. Okay, alpha 2 beta 1. Okay, and these are combined. Okay, and these will explain the spin state, and there is a normalization factor for this one, that is 1 divided by root 2. So that is the third possibility, sigma g1 sigma g2 1 by root 2 alpha 1 beta 2 plus alpha 2 beta 1. Okay, and then we have to write the last possibility. The last possibility is that the fourth possibility, that is sigma g1 sigma g2 and then 1 divided by root 2 under the root 2 alpha 1 beta 2 minus alpha 2 beta 1. Okay, this is another combination. This is both of these are the linear combinations, but here we take the addition and here we take the subtraction. Okay, so there are four possibilities like that, and in these two cases, even if you are taking the square, okay, after taking the square of the electron, you are taking the square after the electron exchange, then the value of the square is not going to change. Here when you are taking the square of the function here before exchange, it will be alpha 1 square beta 2 square plus alpha 2 square beta 1 square, then 2 alpha 1 beta 2 alpha 2 beta 1. Okay, or after exchange also you can take the square, then it will be alpha 2 square beta 1 square, and then alpha 2 square beta 1 square plus 2 alpha 1 beta 2 alpha 2 beta 1. Both of these are same. Okay, if you have any doubt, I will write it here. This is after exchange you can take the square. Before exchange you can take the square. Before exchange the square will be I am taking the square of only what is inside the bracket. Other things are okay, because the other things are not going to change. Okay, so the square before the exchange is alpha 1 square beta 2 square plus alpha 2 square beta 1 square plus 2 alpha 1 beta 2 alpha 2 beta 1. Okay, this was the square before exchange, and even if you are exchanging electron 1 and electron 2 between these spin orbitals, then you will get the square like alpha 2 square beta 1 square plus alpha 1 square beta 2 square plus 2 alpha 2 alpha 2 beta 1 alpha 1 beta 2. Okay, so this is a square. You check both. Alpha 1 square beta 2 square is already here. Alpha 1 square beta 2 square. Okay, it's already here. Then alpha 2 square beta 1 square. Alpha 2 square beta 1 square. It's already here. And then 2 alpha 1 alpha 2 beta 1 beta 2. 2 alpha 1 beta 2 alpha 2 alpha 1 beta 1 alpha 2 beta 2 is already here. So these terms are also same. So it means that after take the square is same before and after exchange, right? So this does not pose the problem that we specified in the beginning. So this is one possibility, and this is another possibility. Here also the same. You can do this mathematics your own. Okay. So we have four possibilities here, and out of this, which one we will take? Then comes to play the Police exclusion principle. And Police exclusion principle says that for a system of two or more electrons, the complete wave function, including the spin, must be anti-symmetric with respect to interchange of any two electron positions. Means when you are interchanging the electron positions, okay, between the spin orbitals, then it should be anti-symmetric. Means when you are exchanging between 1 and 2, then before exchange, whatever may be the function before exchange, that should be the negative of the function after exchange. Okay, so we can check what will happen after exchange here. In the case of the first possibility, what is the function that you are getting? Okay, here, if here after exchange what we are getting is sigma g2 sigma g1. Okay, sigma g2 sigma g1, that's okay. Sigma g2 sigma g1, we can also write sigma g1 sigma g2 because the order of the terms is not important here. Then after exchange, then alpha 1 will be exchanged with the alpha 2, therefore this will be alpha 2, and that will be alpha 1. So this one, sigma g1 sigma g2 alpha 1 alpha 2 is equal to sigma g1 sigma g2 alpha 1 alpha 2, means after exchange nothing happens, you get the same function. So okay, no sign is changing, the sign of the wave function is not changing, so this is not anti-symmetric. Okay, if it is anti-symmetric, then the sign of the wave function will change. Here what will happen if you are exchanging the electronic positions? There also you get one function, that is sigma g2 sigma g1 then beta 2, beta 1. The function remains the same and the sign is not changed. Okay, and here in the third case, if we are exchanging the position in the third case, then what will happen? Then we will get the third one after exchange. We will get sigma g2 sigma g1, then 1 divided by root 2, okay, alpha 1 beta 2, then after exchange it will be alpha 2 beta 1 plus then alpha 1 beta 2. Is there any change? Actually, this part, if you are looking at this part, sigma g1, sigma g2, this part is same, sigma g1, sigma g part. Then 1 by root 2. Then only the order is changed. This is alpha 1 beta 2 plus alpha 2 beta 1. Here also, it is alpha 1 beta 2 plus alpha 2 beta 1. Okay, nothing happened. The sign is not changing. The function remains the same. So that is also not anti-symmetric. And what about the fourth one? Here, after exchange of the electrons, it will be sigma g2, sigma g2, sigma g1, 1 divided by root 2. Then alpha 1 beta 2 will be alpha 2 beta 1 minus this will be alpha 1 beta 2. And now you look at this one. I am going to rearrange this one. Okay, I'm going to rearrange this one. Then I can write it like sigma g1 sigma g2. I just rearrange only the terms here. I am just changing their order, that's all. Okay, there is no problem in changing the order because all these terms are multiplied. So sigma g1 sigma g2, 1 divided by root 2. Okay, then I am going to write this one first. Okay, alpha 1 beta 2, but I write like alpha 1 beta 2. Okay, alpha 1 beta 2, and I have a negative sign here. Okay, I have kept that negative sign out, and I multiply that negative sign here. Okay, I am keeping that negative sign out. That is why I kept positive here. Then I am going to write this is actually positive because I have kept one negative sign out. Then I have to keep negative here because negative into negative will be positive. So this will be negative alpha 2 beta 1. Okay, so this is equal. Instead of writing like this, I can write it like this. So after exchange, the function what I am getting is minus sigma g1 sigma g2 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. What is that? You look at this fourth function. This is sigma g1 sigma g2 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. The negative of this fourth function is this one, right? We have a negative sign here. So after exchange it is negative. It means that it is anti-symmetric. So this is anti-symmetric function, anti-symmetric. So out of the four possibilities, according to Pauli's exclusion principle, only one function which is possible is the fourth one. First three, 1, 2, 3 can be discarded because it is not going to obey the Pauli's exclusion principle. Okay, so we will strike out all these. Okay, 1, 2, 3, these are not possible. Only the fourth one is possible according to Pauli's exclusion principle, and this is an anti-symmetric wave function. So actually psi is equal to, in our case, psi is equal to sigma g1 sigma g2 1 divided by root 2 alpha 1 beta 2 minus alpha 2 beta 1. Okay, this represents the psi. Okay, so this represents the wave function for the hydrogen molecule as a first approximation. Here we have used, you have to know that here we have used the sigma g orbitals. Actually, the sigma g orbitals expressions were obtained from the H2 molecular. Okay. So this is how we have constituted the anti-symmetric spin function. Okay. So We can also write it like a Slater determinant. You can consider like this. The sigma g is in this case here the sigma g is defined as, you already know the definition of sigma g, 1 divided by root of 2 into 1 plus s, okay, 1 as a, 1 as a plus 1 as b, sorry, 1 as a plus 1 as b, 1 as a plus 1 as b, okay, and therefore we can write like sigma g1, actually sigma g1 is actually 1 divided by root of 2 into 1 plus s. 1 as a 1 means in the 1 as a orbital electron 1 is occupying, okay, 1 as a 1 as a 1 plus 1 as b 1, okay, 1 as b1 because it is for the electron 1, okay. This is sigma g1, and sigma g2 is defined as 1 divided by root of 2 into 1 plus s, 1 as a, 1 as a, here the electron is 2, 1 as a 2 plus 1 as b 2, that is sigma g2, okay. So we have defined the sigma g1 and the sigma g2 in this expression, okay, and we know that in this case after exchange psi will become minus I, but you know that psi square is equal to minus I the whole square, so therefore the probability density is not going to change, okay. So that is our wave function. Now what I am going to do is that I can express this wave function as a Slater determinant. I will show you how to do that. Psi is equal to, we already have psi is equal to 1 divided by root 2, because 1 divided by root 2 is a multiplication factor that I can take it out, and so I conveniently write it like 1 divided by root 2 sigma g1 sigma g2 alpha 1 beta 2 minus sigma g1 sigma g2 alpha 2 beta 1. I just expanded the expression for the wave function, that's all. You know the expression for the wave function. This was the expression for the wave function, this one, right? I just expanded this wave function. I multiplied this with the terms within the bracket, that's all. So this is a wave function, and this one I can write like a determinant because this is equal to 1 divided by root 2, okay. If I am writing it like a determinant, I know that this is the product of the term here, the first column, first row term, and then second row, second column term, okay. We have some positions here. One position is here and another position is here, another one here and another one here, okay. I am going to fill these positions in the determinant, okay. This is the first row, first column, and so what I am going to write there is sigma g1. So I am just removing those bars because that may lead to confusion later on. So I am going to write the first row, first column, okay. That is sigma g1 alpha 1. Then I am going to write the second row, second column element, okay. That is sigma g2 then beta 2. Why I have written like this? Because you look at the first term in this expression. It is sigma g1 sigma g2 alpha 1 beta 2. Actually that is the product of this term and this term. So sigma g1 alpha 1 sigma g2 beta 2, okay. This is a product of this, okay, product of this diagonal, and then minus the product of this and this. Okay, so I am going to write this one here. This is sigma g1 beta 1, sigma g1 beta 1, and sigma g1 beta 1. What is remaining is sigma g2 alpha 2. Okay, so this will be written here, sigma g2 alpha 2. So this is a determinant. Okay, so in order to, instead of writing like this, I can write this in this determinant form, and also I can write it like 1 divided by root 2, okay, into sigma g1, then sigma g1 bar, sigma g1 bar. So what is the meaning of sigma g1? Sigma g1 means sigma g1 alpha 1. Means if the electron has the alpha spin, I am just writing sigma g1. If I am writing sigma g1 here, it is obvious that that electron is having the alpha spin. That is why I am not specifying alpha 1 again. So sigma g1 alpha 1. Here sigma g1 beta 1, right? So it has a beta spin. Okay, so since it has a beta spin, I give a bar here. So sigma g1 bar means sigma g1 beta 1. Okay, electron 1 is occupying the sigma g orbital, and it has beta spin. That is it. That is its meaning. And here I can write sigma g2 alone, sigma g2, because it is alpha spin, and here it is sigma g2, means electron 2 is occupying the sigma g orbital, but it has beta spin, so I can write like sigma g2 bar. Okay, bar, then determinant closed. So this type of determinant is called a Slater determinant. Slater determinant. Okay, this is a Slater determinant. So we have expressed a wave function for the hydrogen molecule as a Slater determinant. Okay, so what we have done here is we just picturized the hydrogen molecular orbital. Okay, and I said that the hydrogen molecular, we picturized the hydrogen molecule, and I said that hydrogen molecule is a 4-particle system. So this system is more complicated because it contains the interelectronic repulsions, and then we define the Hamiltonian. Then we wrote the Hamiltonian as h cap 1 plus h cap 2 plus 1 by r1 plus 1 by r. Here h cap 1 and h cap 2 can be considered as the core Hamiltonian. Okay, because it is the Hamiltonian terms originating from by considering the system as the combination of the H2 plus ion plus 1 electron. Okay, and then we defined the wave functions. So when we were defining the wave function, we also included the spin of the electrons, and then we applied the Pauli's exclusion principle, and I have written like how the wave function can be expressed as a Slater determinant. Okay, so I have given you an idea about the wave function of the hydrogen molecular ion. In the next class, we will learn about the energy of the, not hydrogen molecular ion, hydrogen molecule. Sorry, sometimes I'm making the mistake just by saying hydrogen molecular ion. Actually, I wanted to say hydrogen molecule. Okay, and in the next class, we will learn about the energy of the electrons, the hydrogen molecule. Okay, and thank you for watching. Stay tuned.